Imagine a group of kids playing a game of Find the Shortest Way Home. Each kid only knows how far their direct neighbors live and how far those neighbors say the rest of the town is. By sharing this simple piece of information, the distance to every other kid, they can all figure out the best path without needing a map of the whole town. This is the basic idea of distance vector routing. In a computer network, each router only knows the cost or distance to its directly connected neighbors, and the best distance that those neighbors have reported to reach every other destination. By repeatedly sharing these numbers, every router can build a table that tells it the shortest way to send a packet to any other router. The necessity part comes from the fact that routers are often built to be cheap and simple. They do not store a full picture of the whole network, they just keep a small list of vector of distances. This makes the protocol easy to implement and works well for small to medium-sized networks. RIP Routing Information Protocol is like a postcard that routers send to each other. The postcard has a very simple layout. Command tells whether the message is a request or a response. Version, which version of RIP is used, usually 2. Unused, just filler bytes. Route entries, a list of up to 25 entries, each entry containing IP address of the destination network. Subnet mask. Next hop address, who to send the packet to next. Metric, the hop count, that is how many routers the packet must cross. The metric is the simplest possible. Each time the packet passes through a router, the hop count goes up by 1. If a destination is 3 routers away, its metric is 3. The maximum allowed metric in RIP is 15. A metric of 16 means unreachable, like saying the road is blocked. This simple number makes it easy for even a child to understand. Think of counting the number of street blocks you need to walk to reach a friend's house. Think of a classroom where every student stands up every few minutes and shouts out where they think the nearest candy shop is based on what they heard from their friends. In RIP, each router does exactly that. Every 30 seconds, the update interval, it sends a RIP message to all its neighbors containing its current distance vector table. The neighbors receive the table, add 1 hop to each metric, because the data now has to travel 1 more router, and if the new total is smaller than what they already know, they replace their old entry. This sharing process is called route advertisement. Because the messages are sent regularly, routers can quickly learn about new networks or changes, just like children constantly updating each other about the candy shop's location. When a router learns that a link has broken, it does not instantly know the new best path. It must wait for the next updates to spread the bad news, and during that waiting time, the network may temporarily think a bad route still works. This waiting period is called convergence. If the network is slow to agree, a strange situation called count to infinity problem can happen. Imagine 3 kids of BC sitting in a line, each thinking the candy shop is 1 step away through the neighbor on the right. If the rightmost link breaks, A tells B, I think the shop is 2 steps away. B tells C, I think it is 3 steps away. And the numbers keep getting larger each round until they reach 16, which means I give up, it's unreachable. The numbers keep counting up, hence count to infinity. This can take a long time, causing packets to wander around uselessly. Explanation: to stop the silly counting game, RIP uses 3 tricks. Split horizon. A router never tells a neighbor about a route that it learned from that same neighbor. It's like not saying to your friend, I heard from you that the candy shop is 2 blocks away. You keep that information to yourself. Poison reverse. Instead of simply not advertising the route, the router sends a special message saying the metric is 16 unreachable back to the neighbor that originally gave it the route. It's like shouting the road is blocked to the friend who told you about it, so they stop counting on that path. Hold down timers. When a router receives bad news metric 16 about a route, it starts a timer, usually 180 seconds, during which it ignores any later advertisements that claim the route is better again. This gives the network time to settle down, similar to a child waiting a few minutes before trusting another friend's rumor again. RIP uses 3 important timers to keep the network tidy. Update timer, default 30 seconds, describes how often a router sends out its whole distance vector table. Invalid timer, default 180 seconds, means if a router hasn't heard any advertisement for a route within this time, It marks the route as invalid and sets its metric to 16, unreachable. Flush timer default 240 seconds. After a route is marked invalid, the router keeps the entry in its table for a while before completely removing it. This gives neighbors a chance to learn that the route is gone. These timers work together like a school bell schedule. The update bell rings every 30 seconds, the no news means gone bell rings after 3 minutes, and the clean the desk bell rings after 4 minutes. When a route becomes invalid, the router also sends a poisoned update, metric 16, to its neighbors right away so they can start their own timers. The timers are configurable, but changing them too much can cause instability, just like changing the school bell times wildly would confuse the students. Explanation: the heart of RIP's calculation is the Bellman-Ford equation. Think of it as a recipe that each router uses every time it receives a new vector. d sub x of y equals minimum over v in n of x of open brace c of x comma v plus d sub v of y close brace. d sub x of y equals the best known distance from router x to destination y. N of x equals the set of neighbors of router x. C of x comma v equals the cost to reach neighbor v, always 1 in plain RIP because each hop adds 1. d sub v of y equals the distance that neighbor v reports to reach y. Example: suppose router A has 2 neighbors B and C. B tells A that the distance to network 10.0.0.0/24 is 2 hops. C tells A that the distance to the same network is 3 hops. The cost from A to each neighbor is 1 hop. All computes. Via B, 1 to B plus 2 B's report equals 3. Via C, 1 to C plus 3 C's report equals 4. The minimum is 3, so it records a metric of 3 for 10.0.0.0/24 and sets its next hop to B. This simple addition and comparison is what every router does every 30 seconds. Because the metric can never be larger than 15, otherwise it becomes 16 equal to unreachable, the equation stops the network from growing indefinitely. The Bellman-Ford algorithm guarantees that after enough rounds of updates, all routers will have the shortest possible hop count to every reachable network, as long as there are no loops or count to infinity scenarios. Mathematical note: the algorithm converges in at most absolute v-1 iterations, where absolute v is the number of routers in a loop-free network. In RIP, each iteration corresponds roughly to 1 update interval, so the worst-case convergence time is absolute v-1 times 30 seconds. When you decide to use RIP in a real network, there are practical limits to keep in mind. Maximum hop count 15. Anything farther is considered unreachable, so RIP is best for small to medium-sized LANs or campus networks. Maximum number of routes. A RIP packet can carry up to 25 route entries, but RIP2 can be fragmented, allowing many more routes, still very large routing tables. Hundreds of networks can cause many packets and CPU load. Scalability: because of the periodic broadcast and simple metric RIP, does not scale well to the internet or large enterprise networks. More advanced protocols like OSPF or EIGRP are preferred there. Compatibility: RIP1 only supports classful routing, no subnet mask in the update, while RIP2 adds subnet masks and authentication. Modern devices usually support RIP2, but older hardware may still only understand RIP1. Configuration limits: most routers let you set the timers enable or disable split horizon, poison reverse, and authentication. However, changing defaults too aggressively can cause instability. Use cases: small office networks, home labs, educational environments, or as a backup routing protocol where simplicity is more important than performance. In short, think of RIP like a simple map drawn with crayons. It works great for a few blocks, but for a whole city you would need a detailed digital map. OSPF or EIGRP. When deploying RIP, make sure the network stays within the hop count limit, keep the number of routes reasonable, and use the loop avoidance tricks to keep the traffic flowing smoothly.